I'm making this video just so you have an explanation to the answers in these cluster questions. And now you just have something to refer back to if you ever want to go over it ever again. So we're going to go over the ones we did for homework and the ones we did in class. The other ones I'm not going to look at just yet, but definitely look at these questions for your test because you might see a few on them. So I think it is really good to understand why the answers are the answers, especially if you don't know why. Okay? The first thing I want to say is make sure you are reading everything. Everything, including the directions, the charts, the graphs, every single option, even if you think you already have the answer, read every single option. Reading is very important for this Regents. It's very writing and reading based, okay? So this says, base your answers to questions 1 through 6 on the information below and your knowledge of Earth and space sciences. Modeling Earth's interior. While other planets experience tectonic deformation in the form of volcanic activity, Earth is the only planet currently known to exhibit active plate tectonics involving multiple plates. To gain a better understanding of Earth's interior, scientists have developed models using seismic waves, rock samples, and laboratory experiments. These models assist scientists in the visualization of Earth's complex interior and crustal dynamics. Conditions within Earth's interior cause different substances to be found at different depths. The table below shows the regions within Earth's interior where some substances are found. So this first table right here, substances found in Earth's interior. So it gives you each region, inner core, outer core, lower mantle, transition zone, so that's going from the lower mantle to the upper mantle, and the crust. Remember we learned the mantle is that largest layer, so there's a big difference between the lower mantle and the upper mantle, so they give you a transition zone, okay? Then they give you the substances within each layer. So we learned the inner and outer core are made of iron and also nickel. It also gives you the state of matter. So this iron is solid in the inner core and the iron in the outer core is liquid, okay? So it also gave you that. So here are the substances for each layer. Now, this is a part of the same question. The graph below shows some information about the velocity of seismic waves as the waves travel through Earth's interior. So, velocity of seismic waves through Earth's interior, this y-axis is showing you the velocity. This x-axis is showing you the depth below Earth's surface. This side is also the velocity. It just, I guess they tried to make it easier for you by putting the numbers on both sides. That's fine. You can see it's split up into sections from upper mantle, lower mantle, outer core, and inner core. We are going to learn tomorrow, but if you're watching this at a later time, we already learned that P waves, primary waves, can travel through solids and liquids, but shear waves can only travel through solids. So that's why how we know the outer core is liquid, because the shear waves can't travel through it, but don't worry about that right now. It's showing you have to remember that. It's showing it to you. You can see the P wave traveling through each layer at different velocities, though, you can see. And then it's showing you the S wave traveled through all the layers except for the outer core, okay? And it shows you the velocity. Increasing in velocity in the inner core, it's increasing here, increasing here, increasing here. It's very staggered here, okay? And this is going this way. Let's see if I could draw. Oh, it kind of moved my thing. Okay, it's fine. It's going this way with the depth, okay? How do I erase? Alrighty, and close. Let's look at the question finally. Which row within the table correctly describes the substances found in Earth's interior? Here's the substances table. And the characteristic of that interior layer of Earth. So we're basically ruling out everything that's wrong. You don't even have to know anything off the top of your head. You're using the tables to get your answer. So you have to be able to analyze and interpret these tables, okay? So row A, we have to see. Let's see if row A is true. See how this is telling us row A is an option? So if we're talking about liquid iron, that's the substance. Characteristics of Earth's interior. If it's a layer that has liquid iron, what layer has liquid iron? The outer core, okay? So this is saying the outer core is found in a layer where compressional velocity is greatest in Earth's interior. So now, Here's the compressional velocity in the outer core. The compressional velocity in the outer core ranges from about 8 to maybe like 11, just under 11. Is that the greatest compressional velocity? No. In the lower mantle, it goes up to over 13. So that is obviously not the greatest. So that is not our option. It's not row A. All you had to do is look at the graphs, okay? I know it looks like a lot, but that's really all you have to do. The second one, solid stable iron. Let's see, what layer has solid stable iron? That's the inner core, okay? So what is it saying about the inner core? Found in a layer where compressional wave velocity is approximately 11.2 kilometers per second. So here's the inner core. Here's the compressional velocity. If we zoom in, you can see here's 11. It is about 11.2. So that's definitely a possible answer. Let's move on. Pyroxene in quartz, found at depths of 500 kilometers. What layer has pyroxene and a little bit of quartz? Upper mantle and crust. So those are our layers that range from 40 to 410 kilometers. So is that true? No. You don't even have to know that off your noggin. It's in the graphs for you. You just have to know what they're asking for. Okay? Last one. Magnesium silicates. Let's see, what layer is this found at? Lower mantle. Found in a layer where shear wave velocity is greater than compressional wave velocity. We know if it's VP, that's compressional, and VS is talking about shear. So we were looking at, which one? The lower mantle? Let's look. Compressional is a lot greater than shear. Shear is around 6 to 7, of course, and compressional, basically talking about primary, that's what that P stands for, is around 11 to a little bit over 13. So obviously, shear wave is not greater. That means our answer is B. Okay, I'm going to circle it, or let's highlight it. So that's number 1. That's how we do number 1. Okay, very much process of elimination. Forgive me for coloring with a touchpad? But that's the best I could do. Hopefully you understand that the answer is B. Okay? Now, next one. We are going to skip this one for now. This is a really ugly question, and it's a little bit more complex. So we're going to skip that. I didn't give you that one. It's not going to be on your test. Here is one of the ones we did a little bit earlier in the year, or I guess in the unit, sorry. Tectonic processes are responsible for the formation of many types of rocks and minerals found on Earth. This model below shows some information about different tectonic plate interactions found on and below Earth's surface. So you have a really similar model to this in your reference table. I'm going to pause this and pull up a picture for you. Okay, so here is the picture you have on your reference table. Here's the picture they put on the Regents. This is just like a more realistic version, I guess you can say. And this one has a lot more labels for you. And they show you, look, here are the 2 arrows separating. They're telling you that's a divergent boundary. Okay? So is this. Actually, no. This one doesn't. So this one's actually telling you a whole lot more. Okay. All models of Earth's interior depend on indirect evidence. These models predict the sources of heat in Earth's interior. The substances found in the different layers of Earth's interior determine the possible source of heat in each layer. The core contains elements that like to be with iron, but the mantle and crust contain rock-loving elements. These elements are the source of rock-forming minerals of the Earth's crust. Uranium, thorium, and potassium are unstable isotopes that are examples of these rock-loving elements. Unstable isotopes. Where have we seen that before? In our reference table, when we did absolute dating. Okay, so here is, look, uranium's here, potassium's here. All right, so we've seen that before. These are radioactive isotopes. So when we're looking at the questions, which statement correctly describes a source of heat within Earth's interior? We are going to rule out 2 and 3 because we're not talking about radioactive activity or radioactive elements. We are talking about radioactive isotopes. uranium, thorium, and potassium are radioactive isotopes, okay? So now we just have to see which one is the correct answer. So the first one, radioactive isotopes in Earth's interior decay in the mantle and crust, further driving convection currents that cycle materials. For this option, you have to know where convection currents occur, and it is not in the mantle and crust. Oops. They occur underneath the crust. They occur in a layer called the asthenosphere, and that's what number 4 says. Let me start crossing these out so we can get a better look. Okay, so number 4, radioactive isotopes within Earth's interior decay, correct. Radioactive isotopes decay into stable isotopes. Cycling materials in convection currents, that's true. Formed in the mantle and asthenosphere. If they said just asthenosphere, that would be fine too. They decided to put mantle and asthenosphere, even though the asthenosphere is in the mantle, which is like, I don't know why they put both, but that is true. It's still in the mantle or the asthenosphere. You could say either or. You could say convection currents in the mantle, or if you want to be more specific, convection currents in the asthenosphere. But you're never going to say or see convection currents in the crust. So that's why that's not the answer, and that's why this answer is 4. Okay? That is a really bad highlighting job, but it's 4. How this image could have helped us, you can see the rising magma in the asthenosphere. That's really about it for the picture. This reading helped a lot more, I would say, because it gives you this. Okay, so that's that one. This one we didn't do rock cycle yet, so we can ignore that. This is reverse polarity. You're gonna have, I think, like a couple questions on your test with this one. You might see this exact question. Who knows? Certain magnetic, well, I know, but you guys know. Sorry. Certain magnetic minerals and rocks can record the direction and intensity of Earth's magnetic field at the same time they are formed. Okay? They give you what's going on. You don't even have to remember that. The direction of Earth's magnetic field has reversed several times during Earth's history. These reversals are recorded in the bedrock on the ocean floor. Again, they're telling you all about reverse polarity. The model below shows some information about the age and magnetic polarity of the ocean floor bedrock along the Juan de Fuca Ridge system. So here's the model. Here is an image of the reverse polarity. It's saying everything that's gray is the normal polarity. Anything that's white was recorded and solidified into rock during a reverse polarity. They also have a timeline right here. So if we wanted to see what was the polarity 10 million years ago, millions of years, it would be reversed because it's at white. 6 million years ago, it's at normal. 2 million years ago, it's at normal as well. 4 million years ago, slightly reversed, okay? And it's also saying a long line like this, so these lines that look like nonsense arrows and random scratches, those are all fault lines, okay? So if you want to know what that is, there's a little key right here. Let's look at the questions. Which statement correctly compares locations on the Juan de Fuca model? So, basalt, this one is a very much process of elimination question as well. The basalt at location A is older than the basalt at location B. Okay, so A is right by, here's a ridge, okay, that's what that line is. And they tell you, here's the crest of the Juan de Fuca ridge, okay? So this is a diverging boundary. If it is a ridge, it is a diverging boundary, okay? And A is right by that ridge. What happens at the ridge? New crust is being formed, okay? Here's B, all the way in the outskirts, alrighty? So does that mean location A is older than B? No, location A is right next to the ridge, so this was probably formed, I don't know, a million years ago. B, that looks like it was formed all the way back to 10 million years ago, okay? If it's further from the ridge, it's older. If it's closer to the ridge, it's younger. Bill Nye told us that Harry Hess discovered that, okay? 2, a greater amount of outward flow of energy from Earth's interior occurs at location A than at location B. So let's look at location A. Do we think there is a great outflow of energy right here at this crest, at this ridge? Yes. Magma is going to be pouring out of this ridge. That is an outflow of energy, and it's going to be hardening into crust. Is there anything going on at B in terms of the crust and crustal movement? No, not really. If B was maybe over here at the ridge, sure, but it's all the way out here. So B has not seen anything going on for the past couple million years. A is right where it's all happening. Okay? Here, this dotted line is the ridge. This is where stuff's going on. And as millions of years go by, A is going to also be on the outskirts too. So 2 is definitely and most likely the answer, but let's look at the other ones anyway. 3. The magnetic polarity of basalt at location A is the same as the magnetic polarity of basalt at location B. This one you don't really need to know anything for it because you're just going to use this key. A is on the gray, so that is normal polarity. B is on the white, so that is reversed. So that means they are obviously not the same magnetic polarity. 4. The motion of the tectonic plate is from location B to A. So they're saying that the tectonic plate is going from B to A. That is obviously not true. I did this one in class with you guys, but I still want to show you anyway. We know that this is a ridge. It tells us this is a ridge. What you really need to know for this question is that ridges are at diverging plates. Oof, that's supposed to be an arrow. They're at diverging plates, and that at the ridge, new crust is formed in terms of the other options it gives you. But we know at diverging plates, diverging boundaries, the plates are separating. So that means it's actually going towards B and towards whatever's over here. So it's obviously not going from B to A. It's not true. So that means our answer is C. So let me highlight this real quick before I get off of this. Answer is 2. There's a greater outflow of energy at location A. Sorry, my hand's like dragging across my desk. At location A. All right, 6. Describe how the pattern of magnetic field reversal of the ocean floor basalt shown in the rocks on either side of the Juan de Fuca Ridge is evidence for convection currents in the mantle. So, they want you to talk about the magnetic field reversal, so magnetic polarity, and showing you evidence for convection currents in the mantle. Okay, I'm going to pull up the 3 possible answers you can put, and I'll explain them. Just give me 1 second. Okay, this is from the cluster rating guide. I'm going to show you how you could basically come up with your answer. So the first thing it asks you, describe the pattern of magnetic field reversal of the ocean floor shown in the rocks on either side of the ridge as evidence for convection currents. You need to talk about divergent boundaries with convection currents. So convection currents cause rising magma to reach the surface. Okay, convection currents cause magma to reach the surface. Convection currents recycle materials at the ridge. It is going over convection currents at the mantle. Okay, then it's saying what happens when they get up there, solidifying rock. I'm just going to say that part. Forming basalt, pushing rocks further side of the ridge. This one's also saying pushing older basalt, but it's not just explaining diverging plates. You need to bring up magnetic polarity. So this first one, again, solidifying rock into a certain magnetic polarity and move away from the ridge, forming a mirror image pattern on either side of the ridge. You can say forming a symmetrical pattern, causing just a pattern on either side of magnetic polarity. This one says pushing the basalt with a different magnetic polarity away from either side of the ridge. This one says the pattern of the magnetic field on each side of the ridge is a mirror image. So they're all revolving around the same things. Convection currents cause magma to rise, push the plates away from each other, and also form rocks with different polarities that form maybe a symmetrical image or a mirror image. So you're hitting the fact that convection currents occur and can cause diverging plates, and you're also bringing up the evidence used with magnetic polarity. Alrighty, so I think the short answers are a little bit trickier than the multiple choice, and I also told you all these questions are worth 1 point. So if you fail to mention anything about magnetic polarity, you will not get credit on this question. So just please make sure you are reading everything and covering all bases. Okay, we're almost done. All right, this one we'll go through quickly. Okay. Base your answers to questions 1 through 6 on the information below and on your knowledge of Earth and space sciences. Okay. Plate tectonics. Alfred, we know Alfred. Alfred Wegener was a German geophysicist and a meteorologist who proposed the theory of continental drift in 1912. This theory attempted to explain how similar rock formations and plant and animal fossils could be found on separate continents. So we learned this, and they just told us everything. So we don't even have to remember that. I mean, of course, remember it anyway, but whoever was looking at this cluster didn't have to remember it. Widely dismissed by the other scientists from Wegener's time, continental drift would eventually be accepted and become known as the theory of plate tectonics by the 1960s. The model below shows some information about the position of the continents. So this is saying 3 million years ago, all these continents were together, and there was actually a mountain range right in the middle called the Central Pangaean Mountains. Okay, 300 million years later, present day, they obviously are now split. We got this whole mid-Atlantic ridge here forming the Atlantic Ocean, and these mountains are now split into the Appalachian Mountains and the Caledonian Mountains. Okay, they also have a key here showing distance. So if you took a piece of paper, you drew a line here on the paper, you can measure out like distance, and it'll technically be like on this map 3,000 kilometers. That's like a scale. Okay. 1. Use the model to explain how the Central Pangaean Mountains were separated into the Appalachian Mountains and the Caledonian Mountains. In your explanation, include spatial or a temporal numerical value in which this process occurred. So, what you need to understand is what spatial is and what temporal numerical is. They are just trying to make it hard for you. They easily could have said, you can put it in terms of distance, so you can use this, or you can put it in terms of time. That's it. That's all they're asking you, but they're making it more complicated than it needs to be. So you could do either or. You don't even have to do both. If you wanted to do spatial, you're going to use your key. I'm not going to do it right now because I don't have paper, so let's just go to the answer that's acceptable. This is spatial. Diverging plates separated the continents, creating 2 separate mountain chains. So that's that first part. This is saying how they were separated. How were they separated? Diverging plates. What's the spatial evidence or spatial data we use? If you use the scale, you can put from 5,000 to 7,000 kilometers apart. That would be acceptable. And that's what you'll put. Diverging plates separated the continents, so that's showing what happened, creating 2 separate mountain chains. So they went from 1 mountain chain to 2, obviously, located thousands of kilometers apart. And you are saying 5,000 to 7,000 kilometers apart. That is your spatial evidence. What they mean by spatial, again, is distance. Think like, what's the space, I guess you can say. And if we want to do temporal, they give it to you right here. You don't even have to do any math. Here's temporal. Numerical, mind you. Can't just say over millions of years. Give a numerical value. And they even give it to you. You don't even have to look like in the geological history pages on your reference table. They tell you 300 million years ago, present day. So the acceptable answer, again, here's your temporal numerical value over 300 million years. And here is that other part of the question. The continents are separated by diverging tectonic plates. That's simple. That's how they were separated, diverging plates, and give a value. 300 million years ago, over 300 million years, the plates were separated. A lot of you guys, when you did this, went for 300 million years, and I don't blame you. So that's how you do that one. We did not do this one. Here's another magnetic polarity one. The model below represents the polarity patterns found on the Atlantic Ocean floor over geologic time. The model of polarity patterns of we already read that. Okay, so here is the same key. Just out of curiosity, is it the same ones? Yeah, for both of them, they gave you gray as normal. I wouldn't be surprised if they switched it to confuse you, but there you go. So, block diagram A is showing you from the past, and here is time progressing. So if they wanted to be a little bit more specific for you, they could have said, this is 400 million years ago, this is 200 million years ago, and this is today. But they just said past and present. There is the mid-ocean ridge, mid-ocean ridge, mid-ocean ridge. You can even identify it with the magma rising. And what you need to remember is that these plates are separating. If you forget that, what you can do is go back up to any of the other questions. What does it mean when the magma's there? Oh, it's a divergent plate boundary. If you have like a brain fart and you're like stressing out that you forgot, go look back in other questions. You might even be able to find it on your reference table. Depends. Here's the magma. There's like a ridge. Doesn't really show you on this one, but don't hesitate to look. Okay? So, block diagram A, B, and C. Which statement identifies the evidence for how the past and current movements of ocean crust explain the ages of this ocean floor rock? This again is another process of elimination question. Oceanic crust at the mid-ocean ridge in block diagram A is now the youngest normal magnetic polarity rock found in block diagram C. So that's saying oceanic crust at the ridge. So that's saying this section right here, that gray, that's a terrible drawing, is now the youngest in this diagram in C. So if this one's C, this is the salmon we just saw in block diagram A. These are all the same thing. We know, oh geez, sorry guys, that's supposed to be an arrow. We know that over time, the crust is splitting and getting further and further. I used a terrible color also. Let's try blue. Oof. Oof, oof, oof. I'm trying to go through this fast, but geez. All right, so here is the crust at block diagram A. It's all the way over here now in the present. A lot more crust has formed. Does that mean it's the youngest? No, it's actually some of the oldest. It's all the way over here. It spent its time sitting there, going further and further, and it was formed out of all those layers, one of the last. Okay, and probably didn't have to do all that drawing to explain that, but there you go. So it's not one. 2. Ocean crust at the mid-ocean ridge in block diagram A is now the oldest normal magnetic polarity rock found in rock diagram C. That's definitely a possible answer because here is it found at A, normal, and present day, it's definitely not the youngest, so it's not 1, so it might be 2. Okay? 3. The reverse magnetic polarity rock closest to the mid-ocean ridge in block diagram A is younger than the reverse magnetic polarity rock closest to the ridge in block diagram B. Basically, you just have to understand what they're saying because it's, to me, they're making this sound so much more complicated than it needs to be. All they're really trying to say is that the reverse magnetic polarity rock, so remember it's white, closest to the rigid A, so these two white sections, it's saying that they're younger, so that's these sections right here, than these. Obviously, they're the oldest because they're at the edge, so it's not 3. These two rocks right here, the white section, are here. They're at the edges every single time. So they're never going to be the youngest. Okay? So it's not 3. 4. The reverse magnetic polarity in rock diagram B is the same age as the normal polarity in rock diagram B. No, they form at different times. And if you want to double check that, look again at this reverse polarity question. You can see how they take turns. It's not going to go reverse and normal at the same time. They alternate throughout millions of years. So it doesn't matter if it's in the same diagram, they are never going to be the same age. This reverse polarity white section formed earlier than this one. This is the most recent one. Okay, so that means our answer is 2. All right. I can't remember if I had you guys do this one, but let's do it anyway. We're almost done. Oof. Almost done, guys. Sorry, this is taking forever. One of the pieces of evidence that Wegener was missing to explain was his theory For's theory was the driving force for moving tectonic plates across Earth. The diagram below represents the structure of Earth and the geothermal gradient, which it tells you what a geothermal gradient is. The rate of change in temperature with respect to increasing depth in Earth's interior. Okay? The model is a block diagram of a portion of Earth, so this. Arrows represent motions of tectonic plates. Oh yes, I gave you this one. So, this model is ugly. Why? Because it's like sideways and awkward. So this is showing you the layers of the Earth, okay? This is connected to this model. So this is showing you depth. Here's the crust right here. This line right here is showing you basically crust. So it's 0 kilometers. Here's the mantle. This one is saying the mantle is like just under 1,000 all the way up to like, let's say 3,500. That's how this is measuring stuff. And then you have temperature, like here. I'm looking at, see, like this is like such an annoying graph. It's basically telling you if you're at the inner core, you're going to this line. Here is the temperature, and here's like I'm sorry, I just genuinely can't stand this graph. But lucky for you, you don't really need this one right here. If you want to know distance or depth, it's on here. All right, and luckily for this question, you don't really need it either. Okay, so let's ignore that. This is showing you a little bit of a more detailed section of Earth's layers. So here's the depth, and it gives you like the names, okay? Hopefully you're aware that temperature increases as depth increases. We went over that in the beginning, and I feel like that's kind of a given, especially if like the heat comes from convection currents in the mantle. For the crust, it's just gonna, as you get deeper, temperature is gonna increase. So this is showing you like alignment. This is just talking about temperature. This one's talking about distance. So it's showing you as distance increases, temperature increases. Generally can't stand this graph. Okay. This is a similar image to the one on your reference table, but not exact. This is showing you trenches, asthenosphere, continental crust. Okay, sorry. So here's another model. Continental crust is dividing, blah, 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 blah. Let's just read the question. Which statement, based on evidence presented in the diagram, model, and graph, most accurately identifies our current understanding of the driving force of the theory of plate tectonics? All right. The highest amount of heat from Earth's core is cycled by thermal convection in the mantle, causing lithospheric plates to diverge at mid-ocean ridges. Okay, sorry guys. So, back to what we were doing. We looked at one, the highest amount of heat from Earth's core, which is right, you're going to have a higher amount of heat at the core, is cycled by thermal convection in the mantle. If you forgot about that, here's kind of an example of a convection current. You can see it more like in other models. I guess that's more, you can see in the reference table. Sorry, let me go back. Kind of. All right, well, be aware of convection currents, obviously. In the mantle causing lithospheric plates, which is true, to diverge at mid-ocean ridges, which is also true. Here's an ocean ridge, diverging. That one is in the upper question, but I'm not going to drag it. I'll just continue. 2. The highest amounts of heat at Earth's surface, first of all, already wrong. You're not going to get the highest amount of heat at Earth's surface, okay? A cycle by thermal convection in the lithosphere, wrong again. There's no convection in the lithosphere, it's in the asthenosphere, causing plates to diverge at hot spots. Wrong again. You do not get hot spots at diverging plates. So this question is wrong all around. Bad answer. Not question, answer. 3, or I guess option. Higher amounts of heat in the inner core than in the outer core transfer heat to the mantle, causing plates to diverge at ocean trenches. Technically, that heat, I guess, is going to transfer to the mantle, but trenches are not found at diverging plates. That's why this one is wrong. Again, read everything, okay? Higher amounts of heat in the mantle than in the outer core, already wrong. Heat increases with depth, so mantle is not going to be hotter than the outer core. Transport is absorbed by the crust, causing plates to converge and form volcanic mountain chains on continents. So this one is wrong because the heat's not going to get absorbed by the crust and the mantle's not hotter than the outer core. So 1 is going to be our answer. So let me just, sorry, I promise that's my hand on my desk. Oof, that is a terrible, I'm just going to put a 1 right here because that's a really bad drawing. All right, here is the graph for the next question. Average age of North American continental crust in billions of years. So right here, it's 2.5 billion years. Appalachian Mountains are like about 0.6 billion years. Okay. 1.6 to 1.7. All right, sorry. So 5. Based on evidence from the map, which statement identifies the pattern of the ages of crustal rocks in North America? 1. The oldest rocks in North America are found along the Gulf of Mexico, and the youngest ones are found along the Hudson Bay. Let's check it out. Gulf of Mexico, already wrong. Okay. Hudson Bay, sure. No, sorry, that says youngest. No, both are wrong. Youngest, oldest. So if it was flipped, sure, but it's not. It's wrong. 2. The central region of the continent chain. Sorry, I can't read anymore. The central region of the continent contains the oldest rocks, while the youngest rocks are found along the Atlantic and Pacific coasts. Central region, oldest rocks. Here's the Atlantic Ocean, so that means this is the Atlantic coast. This is the Pacific Ocean. This is the Pacific coast. Looks right to me. 3. The oldest rocks are found in the Appalachian and Rocky Mountains. Here's the Appalachian. Here's the Rocky Mountains. Definitely not the oldest. 4. Rocks of the same age are found along the entire coastline of North America. So here's the coastline. The coast is just the edge. So these coasts are pretty similar, but then when you get to up here, you just have to know this is all North America. We're not just looking at America. We're looking at North America as a whole, and you see some really old rocks up here on this coast. So that's why this is not the answer. So the answer to this one, I think we said, was 2. Central regions, the older rocks, while the younger ones are at the outskirts. This, again, is a very process of elimination question. A lot of these are like that, but you just have to read. I'm going to put a 2 right here. Oh, I'm going to put a 2 here because 2 is not good. You just have to read a lot, okay? I believe this is, we didn't look over this one. Okay, that should be all of them because down here are the moon ones we did a little bit ago. Sorry this took literally forever, but hopefully if you just want clarification on one question, you can just skim around and look at the explanation. But overall, it's reading, using the charts and readings to your advantage, and being as descriptive as possible. Make sure you're covering all bases, like especially on a question like this. Alrighty. Expect a few of these on your test. Good luck. You got this. If you have any questions, please let me know. Don't bore yourself with the whole video. Please just skip around. I probably should have said that earlier, but I will see you guys in class. Goodbye. Good night. See ya.